Hello, and welcome to this presentation of the Rivest, Shamir, and Edelman cryptography system, known as RSA. My name is Andrew, and this is for my course, CYBR7400 Intro to Cryptography. Again, my name is Andrew. I am a father of two, and we're married to my wife, Leah. I received my undergraduate degrees, one for business administration and a second for Business of Science or Bachelor of Science in Computer Information Management, both from Life University in Marietta, Georgia. I am currently pursuing a Master of Science in Cybersecurity from Kennesaw State University located in Kennesaw, Georgia, and I'm very excited to be near the end of my course of study. Some of my motivations for choosing the RSA cryptography system is it is a major cryptographic system in IT. As someone who's currently in the IT field in the application support area, I do have lots of opportunities of working with the application with the algorithm itself, but never really knew too much about the inner workings of RSA, and was an opportunity to get to know a little bit something about something I get to work with. My second motivation is going to be to educate other users and kind of get others to know a little bit more about um, the asymmetric encryption method known as public key encryption. And then finally, I'm looking to use this knowledge that I've gained, through the process of research and being able to present it to leverage this area into potentially landing a new role as a cybersecurity analyst, infosec analyst, or I have been doing a little bit of cloud operations work and work on some certifications in AWS. So looking to take my talents to security and potentially the cloud. Now, just looking through the slides, we're going to look at some learning objectives. I'm going to go ahead and introduce you to what cryptography is and kind of differentiate it between cryptography and encryption. We're going to look at categories of encryption, cryptography. I'll give you a little bit of an introduction to RSA itself. We're going to take a look at the algorithm, and then we'll go ahead and look at some of the areas that RSA is used for, the encryption, method, and how it's utilized in maintaining confidentiality, helping with integrity, used for authenticating data as it's transmitted, and how it's going to be used for non-repudiation. Finally, we'll go ahead and take a look at some of the weaknesses and practical uses of RSA that are currently being utilized in the market today. So again, our learning objectives is we're going to go ahead and look at cryptography and kind of get an understanding of what it is, its purpose, and how it's used. We're going to go ahead and differentiate between cryptographic systems. And then we want to go ahead and get a little bit of an understanding of the RSA algorithm itself. How it operates in order to encrypt and decrypt the data. Finally, again, we're going to look at some of its roles in confidentiality, integrity, authentication, non-repudiation, and we're going to get to know some of its weaknesses, and again, we want to know some of those uses of RSA. So first, what is cryptography? Now, cryptography is a branch of mathematics that specifically deals with transforming data, and that could be pre-transmission, transmit like data at rest, just kind of looking at what kind of math goes into it to obscure this data, so that way, as it's either sitting in a repository or storage media or transversing the internet, over the open internet, people who are eavesdropping in on the communications aren't able to kind of recover the information for that data. Why is cryptography important? Well, again, as data traverses the internet, um, anyone's able to listen in on it. And so what we want to go ahead and do is we want to make that information or that data private to people who are authorized to access it. And so if someone's able to sniff that data as it comes across or is being pushed out, they're not actually able to use it. And with the use of cryptography, this is the creation of the actual algorithms that are used to encrypt the data. And so moving forward, the actual encryption is where the data is transformed from its raw plain text into the ciphertext that will be pushed across the internet. And then, so how does cryptography impact encryption? Well, cryptography is the algorithm, and encryption is the process of actually changing that data from plain text into the ciphertext that goes across the internet. Yeah, and that's done a couple ways. All right, so the types of encryption that you'll normally see is two types. You'll see a symmetrical encryption method, and that's a process where a single key is generated, and the one key is actually used for both the encryption and the decryption of data. So just kind of taking a look at the example, if we look at the single key, it'd be like if the key, along with the algorithm, was used to actually encrypt the data, the plain text, and then it's turned into a cipher block, right? And so this one key would be used to lock this data and sent across the internet. Now, once it gets to the other side, again, the receiver is going to use that private key, that secret key, as it's known by in symmetrical encryption, along with, the inverse operation algorithm to decrypt that ciphertext. And so that same key will be used to unlock the data and turn it back into a readable plain text. Now, the type is going to be asymmetrical encryption. Now, this is a different process where two keys are created. You have an initial private public key and a private key. So in this instance, we have our guy who generates a private key and is used to encrypt using the algorithm, turning the plain text into ciphertext. And imagine if this key locks this block of text's ability to be viewed. Now, this specific key is only going to be used to encrypt this information. Now, as it's sent across, you have to have this public key in order to decrypt it. And it does work vice versa. So if this is the private key, the public key, you can encrypt it. And if you send it across, even if you have the public key from another third-party user, they're only going to be able to encrypt it because that's all that key was being used for. And then once it goes to the authorized receiver who has access to the private key, they're going to use that one specific private key to then unlock that block of ciphertext. And again, they're going to use the corresponding encryption algorithm, which in this case would be not the inverse of the encryption algorithm, but it'll be a little bit different. But again, those two combined will then go ahead and result in our plain text being able to utilize it however it needs to be. So now, to actually get into what RSA is. So in 1978, 1977, Diffie-Hellman issued a challenge in order to have a public encryption or asymmetric encryption standard set and created. And that call was answered by these three gentlemen, Ron Rivest, Adi Shamir, and Lynn Adelman. And in 1978, these three who were attending MIT created the RSA algorithm. It's the most widely accepted and implemented general purpose approach to actual public key encryption. And this system is actually based on the factorization of massive prime numbers. And we'll go a little bit more into detail later on about that. So now, just to look at this, so encryption using RSA is really broken down into three general steps. You have the first step, which is going to be key generation. Then you'll have the second step, which is encryption. And then the third and final step is going to be decryption. So just to take a look at the actual algorithm, the first step is we're going to go ahead and select two large prime numbers. Now, we're not going to use prime large ones. We're just going to use a couple examples. And so we're going to use P2 for P, and Q, we're going to use the number 7, both two prime numbers. And then we're going to go ahead and find the product of N by simply multiplying P and Q. It's going to go ahead and give us 14. And then we're going to go ahead and generate the Euler-Toschin. And that is going to be utilized a little bit later when it comes to getting the modulus of our numbers. So now that we've generated our N sum in our Euler-Toschin, we're going to go ahead and try and generate two numbers, E and D, and E is going to be used for encryption, and D is going to be used for decryption. Now, there's three rules that the E has to follow. First, it needs to be smaller than the Euler-Toschin, excuse me, and then it has to be prime, so both E and D also need to be prime, right? And then finally, when we take E and we multiply it by D and we get and we do a mod of the Euler-Toschin, it has to equal to 1. So those are the three biggest rules when it comes to selecting the numbers E and D. And again, if it was a real encryption and decryption, these numbers would be absolutely massive. And that's what makes it so difficult for breaking this cryptographic system. So in our example, we went ahead and we used small numbers. So we chose the number 5. Again, it's prime, smaller than so E has to be smaller than the Toschin. And then normally D, the decryption key, will be significantly bigger than our encryption E variable. So we've gone ahead and selected two of those, and we see how those numbers replicate across. So now that we've gone ahead and generated our public and private keys, we're going to go ahead and follow an example. So the first thing we're going to do is we're actually going to go ahead and send our recipient, which is going to be over on this side, a message. It's going to be the answer to a question that they asked. So they asked, what's the answer to number 25? We're going to send them B, right? And so our value of B is actually going to be, we're going to convert that to a numeric value, and that's going to be the number 2, right? So message is going to equal the number 2 converted from B to a numeric value of 2. We're going to take that 2 and we're going to raise it to the power of our public key, which is going to be 5. 5 to raise to the 5th power is going to be 32. And then we're going to go ahead and mod that times our N value, which was that 14. So 14 goes into 32 twice, leaving us a remainder of 4. And so our ciphertext is going to equal a value of 4. And when we convert that back to a letter value, it's going to equal the letter D. So when we send this message back to our recipient, the letter D is going to traverse the internet, right? And so our recipient's going to receive our value of D. They're going to go ahead and convert that back into a numeric value. And then using our decryption algorithm, they're going to take our ciphertext value of 4, they're going to raise it to the private key value of 11 that we selected earlier. All right, and so 4 to the 11th power is going to go ahead and equal 4,194,304. and then we're going to go ahead and mod that value by 14. Now, when we do that, it's going to have a mod value of 2, right? And so what we're going to do is we're going to convert that back into our alphabetic value, and that's going to equal our true value of B. So our message that the person received, the encrypted value that they received, is going to equal B, which is our original message. And so that's the inner workings of the RSA algorithm. So now how is this encryption utilized in a sense that it's, what's good for the internet? So first, it provides confidentiality when sending, private data, data that's protected by, you know, different legislative acts like HIPAA, so personal um, like health information. So that stuff sent confidentially over the internet, and it makes it confidential because we have to generate the keys and we're creating encrypted ciphertext to send. And so that confidentiality is derived from the actual encryption of that data as it either sits in a storage media or is actually traveling. So data at rest or data in transit, right? And so again, the confidentiality part is where if it is intercepted by a threat actor or a malicious, someone who's malicious, they're not actually going to be able to utilize that data because it's going to be in an encrypted form. And unless they have the private key, they will not be able to utilize it. So it's basically digital paperweight, essentially. And then, so how is RSA used in terms of integrity? Well, that's a good question. So, what's happened is normally, as the data is encrypted, we use what's known as a hashing algorithm, and so that hashing algorithm encrypts the data, and it creates a hash value which is very specific, and any changes at all that happen to the data, whether it's an added space, the changing of a single character, will completely change our hashing value. And so what we do is we take the hash value of that encrypted message, the hash algorithm, and our private key, and we add those into a message block. And then what will happen is we'll encrypt that whole message block and send it across to our recipient. Now, what the recipient will do is they'll take the message block that we sent that's encrypted. They'll go ahead and decrypt that message block, and from there, they will go ahead and test the private key, and as actually a digital signature, which we'll see a little bit later. And then they'll take the hashed value that they used with a private key, right? And they'll compare that to the value of the unencrypted data. So they'll decrypt the data, they'll hash it again, and compare the two hash values to each other, and they'll be able to see whether any changes have been made. And so they'll be able to see that the data that they received is in its true form. So now, how is RSA used for authenticating and for non-repudiation? Well, first, those keys, they act as a digital signature. So as they traverse the internet and they eventually need to become decrypted, the fact that they're able to successfully decrypt the message going in either direction tells you that whoever sent this message is the actual holder of one of those keys, right? And then so that goes to be our digital signature. So that key acts as a signature during the encryption process. And then the non-repudiation part is, again, specific people will have either a public or a private key. And so if a private key sender is sending it over to the public key sender, well, only one person has access to that private key. And so they can't really say they didn't send that message without kind of revealing that they've lost control of that private key. And so that's one way of RSA being used to basically show that whoever did something has to essentially take ownership of that action. So now, some of the weaknesses of RSA. First is going to be a small plain text attack, as well as a small private key attack, and those two are very similar, just because the value of the text that's being sent, and even the key values that are being used to generate the encryption and like the private and the public key are very small, and so that makes them pretty susceptible to mathematical recovery attacks like a brute force attack, where essentially every potential combination is utilized up to a certain point. And if these values, again, are too small, then with modern computing power, it's pretty easy for a device to go ahead and rifle through these prime factorization possibilities. The second type is going to be a timing attack, and this is an attack where um, information is provided based on how long it takes to both encrypt and decrypt a message. And so while it doesn't seem like it would be that important, it kind of gives the cryptanalysis attacker an opportunity to see what potential options or variables could be used um, to generate both the public and private key. So it kind of narrows down their scope of attack. The third is going to be a chosen cipher attack, and this is where manipulating the private key holder into encrypting and decrypting a specific message is used to more easily find a pathway to decryption. So essentially, the attacker is providing a message to the private key holder to encrypt and decrypt, and they know what the message is. And so they're able to essentially use a mathematical equation to reproduce the original plain text message because they already know what it is. The fourth is going to be a fault-based attack, and this is an attack focused on attacking the underlying hardware and kind of forcing errors, whether it's electrical um, deficiencies that cause signature errors, and allow a little bit easier analysis of of the private key. You can kind of see it as it kind of breaks down the integrity of the algorithm while it's functioning. I mean, that kind of lets it um, be easily have a little bit easier time of manipulating the mathematics to then calculate successfully a private key. Excuse me. Finally, we have a mathematical attacks, and these are basically attacks that guess the product of two primes. And it's almost like a brute force attack, except, kind of goes into it with values that are more realistic instead of just guessing from 1, 3, 5, up until, where we have digits that are, thousands of characters long, keys that are thousands of characters long. Now, there are some ways that you can avoid these. Now, for a plain text attack, we can go ahead and just pad our plain text with additional characters, and that's really just, salting more information. That way it creates a larger value. For a small private key attack, this can be avoided by following recommended key lengths, normally set up by governing bodies like NIST in the US, the European Union Agency for Networking and Information Security, as well as the Government of Canada's Communications Security Establishment. Timing attacks, now those can be mitigated through constant exponentiation of time, and this can be done through that exponentiation of time, adding random delays or what's called blinding. A chosen cipher attack can be mitigated through optimal asymmetric encryption padding. So essentially, we're just creating bigger numbers. The fault-based attack is prevented by a well-placed and monitored physical barrier, basically preventing any wrongdoers from accessing the hardware that the algorithm or the computation is actually being executed on, right? And then these mathematical attacks, which is again, basically using the math to solve the problem by using a specified key lengths, 248 bits or 3072, which is kind of the European standard. That just kind of increases the computational time and reduces the mathematical feasibility of actually cracking that decryption key. Right. And now some of our practical applications of RSA that you might see. First is going to be multi-factor authentication, with uh, passwords being, a major aspect of gaining access into a system by attackers. There has to be multiple uses. Well, we now have moved to using multiple avenues for authentication instead of just a single password or, using your fingerprint, but we have gone to generating tokens to then provide an additional step to authentication. There's an RSA handshake for encryption. Now, this is utilized essentially the same way that creating a public and private key, where the initial connection is built, and a symmetric key, which allows for reduced encryption decryption times because of the mathematical equations and how they operate, reduced computational utilization. So that symmetric key is actually encrypted using a private key and sent via the the internet. And when it gets to the end user, they use a public key to decrypt the symmetric key. And then finally, RSA is being used to secure API calls. Now, API is an application programmable interface, which allows basically systems to contact each other without any human intervention. So it allows kind of an automated process between systems. And that is how RSA is utilized kind of in an automation standpoint. I want to just say thank you so much for um, viewing my presentation, and thank you so much.